Hello everyone, this is chapter 9.3 where we'll be discussing multivariable linear systems. And basically a multivariable linear system is a linear system that involves more than two variables usually. Two variables would just be a two-variable linear system that we saw from 9.2. Here in 9.3 we're mainly going to be focusing on equations, or I guess systems I should say, that have three equations and three variables. You could possibly look at four equations with four variables, but that's a little much to be quite honest. So instead we'll just focus on three with three. Now in this particular problem we have of course these three equations and there's three variables. This is honestly a pretty simple system of equations though, because this is what is called upper triangular form. Notice this lower triangle here is missing. So what's there is this upper triangular piece. That's why it's called upper triangular form. When you have a system of equations in so-called upper triangular form, it makes it very simple to solve because we just basically start from the bottom, substitute this into the top equation, and then keep substituting until we solve for all x, y, and z. So right away, we already have a solution, z is equal to 3. And then into equation 2, y plus 3 times z, which we know is 3 now, is equal to 6. This just says y plus 6 is equal to 6, so if you subtract, you get y is equal to 0. And then plugging this into finally our first equation, we can find out what x is. So if we substitute each of those values in, we get x minus 0 plus 15 is equal to 22. If you subtract 15, you right away get x is equal to 7. So here our solution is x comma y comma z, so-called ordered triple. All right, cool. And if you plug these x, y, and z values back into the original system, you'll see that it'll satisfy each inequality or each equation in the system. Great. Now, the goal really is if you have not something so simple like this, but a more full, if you will, system of equations with three variables and three equations, or even more, we want to use this kind of procedure here that are basically operations, three operations that will produce equivalent systems. So equivalent systems are systems that have the same solution basically. So the first operation is we can interchange any two equations that won't affect the system. Multiply an equation through by a non-zero constant. We've seen that already when we were doing elimination from 9.2. We did that a lot. 3 we also kind of did. We're going to add a multiple of one equation to another equation. But the whole purpose of these is that we're replacing equations with these results. So equation 2 would be replaced with multiplying it by 3. That would be using this one. Adding equation 3, let's say multiply by 5 to equation 2, and replacing equation 2 with that result, that would be using this operation. Now the process of using these row operations, or I guess equation operations, into I guess a scenario like this where we can convert any system in this so-called upper triangular form and then solve by back substitution is known as Gaussian elimination. Named, of course, after the famous mathematician Gauss. And now we're going to actually take a look at a particular problem where we have, well, a system of equations that's not as simple as this. We'll use Gaussian elimination, or at least these operations, to convert it into an upper triangular form like this, and then we'll back substitute, and that whole process is Gaussian elimination. So let's take a look at that right now. Right, so now given this system of equations here, we want to convert it using those operations that I explained previously into the so-called upper triangular form. Now the thing to notice is that we kind of have these column setups, all x's, all y's, and all z's, so we kind of see what's going on. I've even labeled the equations 1, 2, and 3. And remember that we basically want an equation involving only x, y, and z on top, only y, z in the middle, and only z on the bottom. Now that isn't necessarily always going to be the case. You could make it however you want, but the whole point is that there are three variables on top, 2 in the middle, and then 1 on the bottom. It doesn't necessarily have to be x, y, z, and z. It could just be, for example, x, y, z, x, z, and y, or something like that, or x, z, and z, I guess. But in any event, let's see if we can make the exact what we had before happen. Now the first thing we'll notice is that we need to eliminate x in two of the equations because two of the equations will not have x. So what I'm going to do is I'm going to pick one that has x with no number in front, and I see it's this one. So I can multiply it by 3 to eliminate with the second one, and then multiply by -2 to eliminate with the first one. So let me do that. So I'm going to pick equation 3, multiply that by 3, add that to equation 2, and that will replace equation 2. Okay, this is probably not the best notation, but it certainly gets the job done as far as what we're trying to do here. So let's see, 3 times equation 3 is going to be 3x minus 3y minus 15z is equal to -9. And then we're adding that to equation 2, which is 3x plus 2y plus 6z is equal to 1. So the second equation didn't get changed at all. And now adding straight down, the x's cancel, and we get -y minus 9z equals -8. Now notice we can multiply any number by an equation. So we can multiply this by -1 to get rid of the negatives, but I don't think I don't think we have to do that right now. It's fine. So this system of equations is now, well, the bottom one has stayed the same, and the middle one has changed slightly. We're replacing it with this. -y minus 9z is equal to -8. Now the only thing is, we haven't touched the first one yet. We can handle that at the same time, actually. So notice what I was saying earlier. We can multiply equation 3 by -2, and then add that to equation 1, and that'll be the new equation 1 now. So let's see. -2 times equation 3 is going to be -2x plus 2y plus 10z is equal to +6. Adding that to original equation 1 is 2x minus 2y minus 6z is equal to -4. And coincidentally, both x and y both cancel, which is lovely. And we get what? We get 4z is equal to 2. Look at that. 4z is equal to 2. And now we're actually set. All we really need to do is, well, interchange these to have it in the exact form we're used to, and then we can back substitute. In fact, we could really just solve for z here by dividing by 4 to get 1/2, back substitute to find y, and then back substitute to find x. So let me erase this and we'll show that right now. All right, so just to show the other operations, I've kind of done a few things here. So obviously, like I mentioned, you can interchange them if you want. So I interchanged basically equations 1 and 3 so that they're in this order. I also multiplied through the third equation, well, now a third equation after interchanging anyways, by 1/4 to make this z already solved for. So now we have z already solved for, so we can handle this much like we did the first example we've seen, which is just, well, plug it into equation 2 now. Well, it gives us y, that'll give us y plus 9 times 1/2, which is 9/2, is equal to 8. So y is, let's see, it's going to be 8 minus 9/2. 8 is 16/2. 16/2 minus 9/2 is 7/2. There are a few ways of seeing that, but that certainly works. And now plugging into equation 1, 1 says x minus y minus 5z, 5 times 1/2 is going to be 5/2, is equal to -3. These, of course, combine to -12/2, which is -6. And then if we just add 6 to the other side, right away we get x is equal to +3. So our ordered triple solution is x, comma y, comma z. And do we want to check this? I think it'll be a little, it's not that bad to check actually. And something to notice here is that these all had 2 in common for the first equation. So we really could have divided by 2 to make it more simple. And that happens sometimes where it's kind of too much to look at. And there are certain things you'll see that we can kind of get rid of right away, kind of trim the fat, so to speak, to make it look easier on the eyes. But let's try this. So if we plug it into the first one, 3 times 2, that's going to be 6. That's going to be -7 because the 2's cancel. That's going to be -3 because 6 divided by 2 is 3. So this will be 6 minus 7. So that's going to be -4. Sorry, 6 minus 7 is -1. My mistake. So we get -1 minus 3, and that is indeed -4. Good. For the second equation, that's going to be -9 plus 7, that's 2. And 2 plus half of 6 is 3. But it was -2, wasn't it? Because it was -9 plus 7. So -2 plus 3 is indeed 1. Good. Now for the third one, well, let's see. This is 3. This is going to be -7/2. This is -5/2. Those combine to -12/2, which is -6. 3 minus 6 is indeed negative 3. Perfect. So this is a very, very good example of using those operations. We're going to look at one more, and I'm going to try to explain a different way of doing it, but in reality, this is kind of all we really need to see in this section. So I'm going to show, again, a little bit of a different way of doing it, but it's really the same idea. Just finding equivalent systems, in other words, systems that have the same solution, by using those three operations to get it in our upper triangular form, because remember we have this lower triangular piece missing. This, by the way, is known as row echelon form, but we don't really need to know the vocabulary too much there. And then back substitute. So now let's take a look at one more example to complete this video. All right, so here I describe an alternative way to solve a system of three equations. The only thing is this only works with three equations. Well, kind of. You can extend this idea, or I guess extend this idea to a system of let's say 4 equations, but you kind of have to, well, it just gets more involved. So I'll explain how to do that after the fact, but let's read. So here I say eliminate one variable 2 different ways. And if you do that, you'll basically get a resulting equation for each elimination. So let's say here we wanted to eliminate y, for instance. We're going to do it 2 different ways. So we can do it with 1 and 2, we'll get an equation. Then we can do it with, let's say, 2 and 3, and then we'll get another equation. Step 2 says to solve the system involving those new equations that result from step 1. Once we solve that, notice if y is eliminated, each of those new equations will only involve x and z, actually. So we can solve the system with x and z, that'll solve for x and z. Then, step 3, back substitute the solution from step 2 into the original equation, or one of the original equations, to now find y, for instance. Now, if you wanted to extend this to an equation, or a system of equations that has 4 variables, well, I guess you'd have to modify this a little bit so that you can eliminate one variable 3 different ways to get 3 new equations, solve that system using this method. So it's kind of like reduces to a system of 3 equations. You would solve that using this method to find x, y, and z, and then plug it in to find the remaining w, or whatever you call it. But anyways, let's see if we can proceed using this idea. Again, you can also try to use Gaussian elimination like we previously did, but here I just wanted to show something a little different. Now, here, what do we want to eliminate? Well, notice what I kind of gave us an idea of from the previous example. We look for one that has no number in front of it, like this x. That's something we kind of noticed, that we multiplied it by whatever we needed to match these, and we saw that also in elimination from 9.2. So here, the numbers, or I guess the letters that have no numbers in front, are x and z. So those are perfectly good candidates to eliminate. So if I want to eliminate x 2 different ways, I can multiply it by -2 to eliminate it with equation 2. And then similarly, I can eliminate it with equation 1 by multiplying by -5. But just to spice it up, because I already did elimination of x, I'm going to eliminate z. So I'll eliminate z with, so for step 1, I'm going to eliminate z 2 different ways. So I'll first do with, because I want to use 2 because it has no number in front. So I'm going to do it with 1 and 2. So let's do that first. I'm not going to show too much work here, but notice what to do the elimination, I'm going to multiply the second equation by 2 and then add these together. So 2 times this plus this is 9x. Okay. 2 times this is 8 minus 3 is 5, so that's 5y. 2 times this is -2z, added to this cancels out, of course. 2 times this is 14, 14 plus 3 is 17. So again, I didn't really show too much work, but allow you to verify that on your own. This is the leftover equation we get, and I'll call this equation 4, just so we're kind of organized a little bit. So now I want to eliminate z a different way. So now let's eliminate z with, well, again, I want to use 2 again, so let's do 2 and 3. By the way, we could technically do 1 and 3, because notice, if you multiply the top 2z by -2, you get -4z, and that matches that for elimination. But here I'll do 2 and 3. Good. So I'm going to multiply the top by 4, and then add it to this. So 4 times this is 8, plus 1 is 9x also. Okay. Let's see. So now what? Again, I'm multiplying by 4. So 4 times this is going to be 16. 16 minus 11 is going to be 5y. Oh. This is not looking too good because we're getting so far the same equation. And yeah, it's going to be the same thing. Actually, maybe it'll be different. Let's see. So again, we'll multiply by 4. So 4 times this, that cancels, good. 4 times this is 28. 28 plus 3 is 31. Okay. So now, this is not really the best example, but it's still an example nonetheless. So I'll still use it, and I'll show you what happens. So the second step would be to solve this system. So the second step here is to solve the system with x and y. So the system is 9x plus 5y equals 17, and 9x plus 5y is equal to 31. And what you notice is, well, we actually saw an example of this in 9.2. The left-hand side is the same, the right-hand side is not. So if we just straight up eliminate x, that also coincidentally eliminates y. So adding straight down after multiplying by -1 gives us, well, these cancel out, and we get 0 is equal to 17 minus 31 is -14. And this, of course, is a contradiction. It's not a true statement. So what this tells me is that there's actually no solution. If there's no solution to this system, then that means there's no x and y's that satisfy these. Moreover, there's no x and y that satisfy these. So there's actually no solution to this at all, making it an inconsistent system. And again, that's inconsistent. And that's kind of nice because, again, well, we saw this in 9.2. It's just not good in the sense that our process kind of fell apart. So I feel like we kind of maybe should do another one. I'm going to change this up a bit just so we can see something that will actually show the process a little more. Right, so we're going to try this one last time with this one. Hopefully we get something useful here. Now notice the only letter we have in the number in front is in equation 1, and it's y. So we can multiply by -6 to cancel this one, and by -8 to cancel this one. So for step 1, we'll eliminate y using 1 and 2, and then using 1 and 3. But let's just do one at a time. So if we multiply by -6, let me actually write it down. We get -12x minus 6y minus 18z is equal to -6. Good. And then adding that to 2x plus 6y plus 8z equals 3 gives us our new equation, -10x. These cancel, so -10z is equal to -3. So, I mean, I guess it's okay. So -10x minus 10z equals -3. Great. So now I want to eliminate with, again, the same variable y, but now with a new set of equations, but I want to use 1. So I'm going to use 1 and 3 here. And let's see what we get. Well, I need to multiply by -8, so let me write that over here. Times -8 will be -16x, -8y, -24z, and -8. Good. And then adding it to the original equation 3 gives us 6x plus 8y, so I'm just copying it. 18z is equal to 5. Great. So these give us a -10x. Good. These cancel. Let's see. 18 minus 24, that's going to be 6, -6. -6z is equal to -3. Wow. That's actually really, really good because it looks so similar to this one. Notice -10x and the -3 on the other side. Only these are different. So I think that's actually, we're in much better shape than the last example. So far anyways. So now let me clean up our scratch work here and continue with step 2. Right, so now for step 2, we want to gather these two in a system. So let me write that. And solve that system. And like I mentioned previously, I usually call these equations 4 and 5 just for clarity. So if you want to do that, you can. You don't have to, but it's just a suggestion, I guess. Now in this case, if you multiply, let's say, the bottom one by -1, that'll actually change the signs to all positive. And if you add straight down, notice these cancel and these cancel. We get -4z is equal to 0. Divided by -4 gives you the z is 0. Fantastic. And if z is 0, plugging it back into, let's say, equation 4 gives us what? Well, it gives us -10x plus 0 equals -3. So that means x is equal to 3/10. And now, finally, for step 3 of this process, we can back substitute into an original equation to finally find the other variable we don't have yet, which is y, of course. And you guessed it, I'm going to use the first one because there's no number in front of y, so we don't have to divide by anything at the very end. It's lots of work to do, basically. So now this is going to be, let's see, 2 times 3 over 10 is 6 over 10, which reduces to 3 over 5. So it's 3 over 5 plus y, plus 3 times 0 is 0, so we don't need to write that, equals 1. And this makes y equal to 1 minus 3/5, which is 2/5. Perfect. And now finally we can write our ordered triple as, well, x, comma y, comma z. And if you want to check this, we can certainly check this. I'm not going to do that, but you can do that. And that concludes 9.3. Again, we only saw kind of 3 examples, but really that just shows the process. I gave you 2. Let me just say this. The first way I showed you, Gaussian elimination, will help more for what we'll see later on in chapter 10, because it relates more to something kind of greater. But this process, I think, is kind of helpful because it relates it back to something we saw from 9.2, and we reduce it to a system of 2 equations. So anyways, that concludes 9.3. I'll see you in the next video for 9.4. Thanks for watching. See you then.